In this video, I will provide a short overview of our work on defending CNNs from adversarial patches. Let's begin by breaking down this long title into parts. First, I will describe the problem of recovery of adversarial patches against CNNs, which is the one we are trying to solve in this work. CNN models are deep learning architectures typically used for computer vision tasks such as object detection and image classification. When a clean input image without adversarial perturbations goes into a CNN model, if the model has been properly trained, it will be able to produce an accurate output corresponding to that input image, such as the bounding boxes in this pedestrian crossing example. However, if the input image has been compromised by an adversary using adversarial patches, the CNN model will be misled into producing an erroneous or incomplete output. Therefore, the goal of recovery methods is to intervene in order to undo the detrimental effect that adversarial patches have on the model's output. It is important to note that we don't know beforehand if an image has been affected by an adversarial patch or not, so recovery methods should also prevent intervening unnecessarily on clean images. Let's now talk about Saliuitl, or proposed solution to the adversarial patch recovery problem. I will first highlight the main differences between Saliuitl and existing recovery approaches. First, existing approaches often assume that there will be at most one patch per image, that the adversarial patches will have a square shape, or both. Therefore, when confronted with multiple or non-square patch scenarios, existing defenses might struggle to fully recover the victim model's output. Meanwhile, Saliuitl is able to handle multiple and non-square patch scenarios in the same way that it handles single square patch scenarios. Second, existing approaches usually do not perform an explicit detection of adversarial patches before applying the recovery pipeline. This can lead to problems, especially in clean images, where unnecessarily applying a recovery pipeline might lead to errors, such as the spurious and duplicate object detections in this example. Meanwhile, Saliuitl always performs detection before attempting recovery, therefore maintaining performance in clean images. Finally, most existing approaches discriminate between adversarial and non-adversarial regions using fixed saliency thresholds, while Saliuitl does not, but I will defer the details on this for later. This slide shows a high-level simplified description of Saliuitl. During the detection stage, Saliuitl leverages the output of a hidden layer of the CNN victim model in order to produce a detection score. And if the score is low, then Saliuitl will completely skip the recovery stage. However, if the score is high enough, Saliuitl will perform the recovery stage to undo the effect of the detected patch attack. This two-stage structure emphasizes how Saliuitl always performs detection before attempting recovery. Let us now go through each step in these detection and recovery stages. The detection stage begins by taking the output of a shallow layer of the victim CNN model and aggregating it across channels, yielding a two-dimensional feature map. This is a good point to explain what it means to use a fixed saliency threshold. Consider that for the values in this feature map, we select some saliency threshold, such that all the elements in the feature map above the threshold are considered salient and all others are considered non-salient. We can interpret this as a binary feature map where the elements in this binary feature map indicate the salient elements of the original feature map. What methods relying on fixed saliency thresholds do is then to associate these salient regions with adversarial patches. However, this involves carefully tuning the saliency threshold based on statistics for images with and without adversarial patches. We propose to instead use a set of thresholds spanning the entire range of the feature map. This way, we don't need to tune for a specific threshold, and what we obtain instead of a binary feature map is an ensemble of binary feature maps. Then, we extract NF attributes from each binary feature map in this ensemble, and we aggregate all the attributes across the ensemble into the attribute vector S. We then feed this attribute vector into an attack detector, which is a one-dimensional convolutional neural network that has been trained to perform binary classification on attribute vectors corresponding to clean images and to images with patches in them. This attack detector uses the attribute vector to compute a detection score. The attack detector learns to produce low detection scores for images without adversarial patches and high scores for images with adversarial patches in them. Therefore, only if the detection score is high enough, we move on to the recovery stage. For recovery, we once again leverage this two-dimensional feature map that we obtain from the victim model and a set of thresholds spanning its range, which can be the same one we use for detection or a different one. Recovery is an iterative process where we will use each of these thresholds one at a time. Note also that this set of thresholds is in descending order. Each recovery iteration begins by taking the next threshold from the set and applying it to the feature map, therefore yielding a single binary feature map. Next, we preprocess this binary feature map by removing outliers from it and mapping it back to pixel space in order to obtain a mask that we could directly apply to an image. Then we apply this mask on the initial image where we have detected adversarial patches and we do inpainting of the masked regions. We feed this inpainted image back into the victim CNN to obtain the recovered output for the current iteration. If we identify significant changes with respect to the previous model output, we will then update that output using the recovered output from this iteration. Also, if the mask that we applied during this iteration is too large, we will stop the recovery process altogether. Otherwise, we will move on to the next threshold in the set and start the next recovery iteration. Notice that in both the detection and the recovery stages, we did not need any knowledge regarding the number or shape of patches. We evaluate Saliuitl on single, multiple, and non-square patch attack scenarios against CNN victim models performing object detection and image classification. The figure shows on the vertical axis the best trade-off achieved in terms of clean performance, that is, performance on images that do not have patches, and adversarial performance, which are images that have been compromised by patch attacks. This trade-off is shown for Saliuitl and existing recovery methods, and we find that Saliuitl is able to overall outperform existing methods, and it is also able to better adapt to scenarios with multiple and non-square patches. We also consider an adaptive attacker with full knowledge of Saliuitl, which is able to launch attacks optimized to bypass our defense. This figure shows the recovery rate of Saliuitl and the effectiveness of the adaptive attack for different degrees of stealthiness from the adaptive attacker. We find that as the attack becomes stealthier, Saliuitl's recovery rate decreases, yet the attack effectiveness decreases at a relatively faster rate than Saliuitl's recovery rate. We also evaluate baseline defenses against this adaptive attacker, and we find that all non-certifiable defenses are less resilient to the adaptive attack than Saliuitl, even though the adaptive attacker has no knowledge of these baseline defenses. Please check our paper and our code for further details on Saliuitl's implementation and evaluation, and do not hesitate to reach out.